I'm sorry for giving this talk, by the way. How do we get undergrads to do high-quality computational spectroscopy research? First, this is a video I made, quantum chemistry for high school students. I teach Hartree-Fock, configuration interaction, coupled cluster, all using high school level concepts. Then I show how to set up an input file, run calculations, things like that. All the students in that video, they all go home, they all start doing calculations, they all build potential energy surfaces for a bunch of molecules. The next week, we go to the next stage, quantum chemistry and machine learning for primary school students. We make the input files more complicated. The first one, all those potential energy surfaces, they're doing it with default settings. You know, for O2 molecule, they just type O2 and the bond length and CCSD, and then they get an energy. Now we actually start to specify spin states. Is it a singlet or a triplet? Frozen core approximation. How many electrons do you want to freeze? And why is this for primary students? This entire video is catered towards primary level students. 8-year-olds can be taught, 8-year-olds can be shown a periodic table and shown how to count the number of electrons and how many are paired or unpaired and calculate 2s plus 1, right? So the whole video is catered to the primary school level. You don't need to know calculus to watch this video. And if you guys think this is crazy, it's you that's crazy. Because in these videos, you can see the students are answering questions, they're understanding. I don't go to the next slide until they have understood the present slide. And you can even see at the beginning of this lecture, you can see all the potential energy surfaces that the students made from the high school level lecture. Okay, so I had put out this internship advertisement. The portal closes 48 hours after you put out the advertisement, and you can see we had 417 applications for 10 positions. We can take all 417 applications. We can take all of them. We can take all applicants. Because applicant 1 works on molecule 1, applicant 2 works on molecule 2. We can do hundreds of molecules, all with the same number of nuclei, similar number of electrons, same spin, same point group. And then they're all in the same Discord server, communicating with each other, helping each other, asking questions to each other, not necessarily to me. One of them might say, oh, my Hartree-Fock didn't converge. Did anyone else have this problem? One of them says, oh, well, it happened to me too, at cycle number 30. So I increased the number of iterations to 50, and then I actually got a lower energy. And they're all helping each other out. So, you know, you can have thousands or hundreds of thousands of students all doing, there's enough molecules for everyone, right? And this was just in round 1. We ended up doing several rounds of this. Here's another exercise. We had a pre-undergrad student. This was a high school student, grade 11, junior year, or whatever you want to call it. 16 years old, hadn't even started applying for universities yet, working on molecule 1. Undergrad works on molecule 2, pre-grad, pre-doctoral student, doctoral student. Everyone's working on similar molecules, same number of electrons and everything. I don't have enough time to get into all the details about everything. I'll say that the the grade 11 student, 16 years old, actually made the second, the second furthest in this exercise out of everyone. And you might be seeing her next year at ISMS. There's 2 professors, one from Brazil, one from India. That's just because these happen to be the people that reached out to me saying they wanted to collaborate. I didn't advertise this, so if you're wondering why do I not have anyone from my own country, Canada or USA or whatever, I just didn't advertise. Now that I think about it, you know, if anyone is brave enough to participate in something like this, my email address is on the last slide. So like everyone, I'm going to start by saying that my first talk was at ISMS when it was in Ohio. This was work done as a second-year undergraduate student. My supervisor was Bob Leroy. And, you know, anyone can give a talk, right? But is this stuff actually important? Well, it turns out 20 years later, almost 20 years later, this is being used by a lot of people. We built a potential energy curve using spectroscopic data, and now anyone that wants to work on this molecule is using that curve. There's people at UBC making optical lattices out of lithium-2. There's people trying to use them as qubits for quantum computers and stuff. And it's the simplest homonuclear molecule that's not charged and has a stable ground state after H2. So helium-2 is not stable in the ground state. So anyway, it's a high-quality potential energy curve, and you know the DE and RE. Years later, I look into CRC handbook, and if someone wants to know how how long is the bond in lithium-2, this is what they get, the reference to that paper. So it is, you know, you don't need to have 5 years worth of spectroscopy courses to do this type of work. It takes a long time. We presented it, and we didn't publish it in a journal until 4 years later because we kept improving the potential. You can always make it better and better. But it is publishable work. Peter Tony has called this a masterpiece in 2019. But anyway, I just wanted to say, like, a lot of people, this was an undergraduate talk, I was very nervous as a second-year undergrad. A lot of people came to me afterwards saying, oh, you should have put in a nomination for the Rao Prize. But the Rao Prize, at the time I register for the conference, and it says this is only for graduate students. They're trying to scare away the postdocs from going into it. But there really should be a Rao Prize for undergrads. And I'm going to go into that in a bit of detail later. But so, sadly it was only for grad students at the time. I think it still is. And I could have pretended I was a grad student and compete against fourth-year grad students that have been giving talks at ISMS for the last 6 years, who have they're just done their thesis and have several publications already and have experience and all that. But you can only go for it once. And I actually left spectroscopy for my PhD. I left the group and started working on other things. But I'll just say that due to the success of that talk, Bob Leroy and then later myself, we actually had a lot of undergrads presenting at ISMS after that. And all of these ones actually also contributed to talks, but these ones actually presented at ISMS. And so, but again, like a lot of people like at these, really prestigious research-based institutions say, okay, these are undergrad projects, but this isn't as profound as something where you're doing 5 years worth of work on something and you have such high level of knowledge after taking all these graduate level courses. But I want to say that Bob Leroy was a top-tier full professor at a top-tier research university, probably the best research university in Canada for the type of work he was doing, which was computational science. Published more high-impact papers than most people at this conference, 30-plus papers with 100 citations. He wasn't publishing cancer research or nanotechnology. It was molecular spectroscopy of diatomics and stuff, so they don't usually get a lot of citations. But only 2 of these were with PhD students. And he had 3 PhD students in his 46 years, 1972 to 2018. 46 years as a professor, 3 PhD students. The third one, his most cited paper, was 39 citations. So the vast majority of his work was, a lot of these 30 papers were actually done by undergrads, done with the help of undergrads. A very prolific researcher in his field, probably the best at what he did, which was building potential energy curves from spectroscopic data. And the best work was done without the help of a long-term 5-year PhD student. You know what I mean? So now let's talk. I want to talk a little bit about my work, and because I left spectroscopy, I started working in quantum dynamics for my PhD, then quantum computing, group theory, genomics, computational complexity theory, combinatorial optimization. And I don't have access to PhD, the type of funding for PhD students and stuff. My access is undergrads, high school students, primary school students, that kind of thing. And I don't have so much time in a 15-minute talk to talk about my recruitment methods, how I choose projects, supervision techniques and stuff. So I'm just going to show off all the amazing work that these undergrad students have done. So my work was in quantum dynamics as a doctoral student. There was dozens of papers on this FMO complex. Everyone's trying to calculate the quantum dynamics of the FMO complex. They all published the same. They even use the same colors. These are all from different publications. Everyone's doing the same thing. They're all getting different results and comparing it to each other. Towards the end of my PhD, David Wilkins was towards the end of his undergrad degree, and we did the first exact quantum mechanical calculations. And we found that all these approximations that ignore quantum coherence or don't ignore quantum coherence, we found that quantum coherence didn't make any difference in the final results. So we published this paper, Why Quantum Coherence is Not Important in the FMO Complex. That put an end to a 10-year debate about this topic. A lot of famous professors, Graham Fleming, Greg Swoles, all these guys thought that quantum coherence was like, the people are saying that the bacteria is a quantum computer when it's doing photosynthesis, it's actually carrying out a Grover search, all these things, but it turns out all that stuff is not true, and 2 years later this was even confirmed by a much bigger group, led by Dwayne Miller, who's a director at the Max Planck Institute with more funding than most countries have GDP. And the title is the same, Nature Does Not Rely on Quantum Coherence in the FMO complex. David Wilkins was an undergrad student, now he's a faculty member at Queen's University Belfast. Nathan Bryans finished his undergrad, reached out to me, says, I need a letter of reference for my grad school applications. Also, I'm looking for some temporary work or contracts. I said, okay, this paper in PRL was just published 2 years ago, 2012. They made this table, and from that table, they derived a Hamiltonian whose ground state encodes the solution to the factorization of 143. 11 times 13, you'll get those numbers in binary in the ground state of the Hamiltonian of this quantum computer right here with 4 qubits, 4 hydrogen atoms, 4 nuclear spins. They can all be up or down. That's a 0 or 1. Just like your classical computer stores information as zeros and ones, here you're storing your information as zeros and ones, up, down, 1, 0. But these zeros and ones can be in a superposition. They can be 1 and 0 at the same time. So this is a quantum computer. They factored 143, and I told them, okay, write a computer program to automate the process of building this table, and then run that computer program on some bigger numbers, and let's see if we can factor bigger numbers with 4 qubits. And this was the program, and the output, a slightly larger table than this one, made by the computer, and we factored the number 56153 with 4 qubits. And he is now Director of Artificial Intelligence at ATB Financial. And I think this is interesting. 18th of September 2014, he sends me the email. October, I'm presenting this at universities. November, I'm presenting it at conferences. Late November 2014, I submitted it to arXiv. December 1st, it's published on arXiv. Only took until December 1st because I delayed it for a few days while I'm fixing some typos and stuff like this. But phys.org picked up on it. New largest number factored onto quantum devices, 56153. They didn't know it was just an undergrad doing that stuff. This is published all over the world in other languages and stuff. Ronald Rivest, the R from RSA cryptography, he cites, he talks about Peter Shor, and then he talks about us. And that, because of the success of this quantum computing project, I recruited more undergrad students. And Emil Okada was a first-year undergrad student. Richard Tanburn was a second-year undergrad student. They both came up with their own methods for reducing the number of qubits required to factor numbers. So this is not just like, okay, we know we have software for building potentials. Give you 1,000 molecules, you build 1,000 potentials, not this. They came up with methods to reduce the number of qubits required in a quantum computer to do this task. Methods that didn't exist before. Emil Okada is now a professor of mathematics, doing much better than I am. And Richard Tanburn got a permanent position much earlier than I did. And he got a permanent position doing research at Google's DeepMind. He published this paper with Google's DeepMind, Advancing Mathematics with AI. The most boring title for you guys, right? Like, you guys are bored of this. Everyone's talking about it. Here on the radio, they're saying that this math professor spent 10 years trying to do this proof, and ChatGPT did it in a minute or something. However, this is 2021, 2 years before any of you had heard of ChatGPT. And this guy later on went on to get one of the most controversial Nobel Prizes in history. Anyway, this was considered the biggest breakthrough in mathematics in 2021. This was the highest voted answer to that question. I want to now talk about spectroscopy again, because I have this first-year undergrad student who answered this question: what are the possible point groups for a molecule with a certain number of atoms and a certain formula? Seems trivial. Like, you guys probably, oh, I already answered that in my undergrad class. No, you didn't. This is a table everyone's probably seen in the Peter Atkins physical chemistry book, and in one or two other papers. Longwood-Higgins has a table like this. There's problems in those tables. In the Peter Atkins one, there are problems, and those are all fixed in this. This is the perfect version of that table, but that's just, you know, that's not a big deal. This table, also not a big deal. All of you guys can do this in your undergraduate class. Triatomics can have 3 different formulas: A3, A2B, ABC. There's 5 possible point groups if you have only 3 atoms. A2B, like H2O, cannot be associated with a D3H point group. You can make this table yourself. Even for 4 atoms, you can make this table yourself. You might not get to this. Once you do this for 4 atoms, it's going to be exhausting by the end. You might miss a couple. It took quite a few iterations before we finally, in this paper, we actually have that table, and it's finally complete. But that itself isn't such a big deal, right? Any undergrad can do that. But we did it for n atoms, and so if I give you a formula like A3BCD2, I can tell you that unless it's planar or linear or something, it either has to have D3D or D3 point group if it's not C1. So instead of doing that big flow chart, I can tell you now, based on the formula, these are the only possible point groups. Based on the point groups, these are the only possible formulas for a certain number of atoms. And I contacted every author of a group theory textbook and every group theory instructor I ever knew, and everyone said, I've never seen anything like it. So even though this seems like such a simple thing, no one had done it before. And you don't need 5 years of PhD experience to solve this problem. You just need the patience and the work ethic and the motivation and everything. So I do have to just talk about, when I practiced this was like 35 minutes, so I still have 27 seconds. I have to talk about 2 more undergrad students because they didn't get an opportunity to publish or present these works. Toby Cathcart-Burns, second-year undergrad student, another 2012 PRL paper. He generalized this paper to work on multi-color Ramsey numbers and directed graph Ramsey numbers. And he was a part-time volunteer undergrad student, taking courses full-time during the day, working a little bit in the evenings. And in a few weeks, he managed to generalize what these guys did in this PRL paper. But more importantly than that's the and here. The PRL paper has this huge proof. He wrote a one-line proof for all of this and a much stronger version of it. And you won't believe it. In 15 minutes, I can't tell you everything. But the only reason why we didn't publish this is because we didn't want to piss off the author. Now it's 11 years later, we can, I started working on this talk and I think, okay, we should now publish that. And same with Eric Huang. I don't know if you've ever heard, there's $1 million problem in computer science about proving whether P equals NP. And that problem was first proposed by Jack Edmonds in the 1950s. And he's also the person responsible for the idea that polynomial time algorithms are efficient and exponential time algorithms are in a completely different potential computational complexity class. And since the 70s, he's been asking everyone to code this optimal branching systems thing. And Eric Huang finally did it as a second-year undergrad, working full-time at a different internship somewhere else, but part-time with me in the evenings, and he had volleyball on Wednesdays, and really busy guy, but managed to code this, got it working. Only reason it's not published is because with these undergrads, they get busy. When the courses start, then they just get very busy. And 4 years later, I contacted him last night while I was preparing these slides, and he's still doing well, and I think we're gonna go publish this now. So the HPQC Discord server, 124 people survived over the last 3 years. 8 of them were online at midnight when I was working on these slides. And I just wanted to show you, like on the side, we have all the different channels: Malcast, C4, Gaussian, PySCF, NWChem, Sci4, MRCC, MATLAB, Avogadro, group theory, special relativity, geometry optimization, graph theory. Different channels to talk about different things. If you have questions about C4, all the different students, they're talking about they're helping each other out, they're debugging things together on Discord, right? And this is just an example of one of the channels and one of the people, June 2026, just this month, showing me some results. And so with that, I thank you for your attention. Anyone can join this Discord server. You just need the link and a camera to take a picture of the link. And this is my GitHub page and my email address. So thank you so much for your attention. I can't believe that I finished it in less than 18 minutes.
Okay, time for maybe a question or two?
29 seconds.
29 seconds for a question.
So your students, did they participate in the Regeneron Prize?
In the what prize?
The school kids. In this country, there is a Regeneron Prize.
I've never heard of it.
Oh, because I had a student who actually was a finalist and got $29K.
$29,000!
He was a finalist, but the first place was like $150,000.
All of my students should have registered for that. I never heard of it.
It's called the Regeneron Prize.
Yeah, and we have to make a RAW prize for undergraduates.